And so, yeah, my talk will be about the role of GNSS station metadata, actually, to differentiate from the previous talk. And I would like to thank the chairs for inviting me to give this talk. This is actually not a formal IGS activity. It's research we do on our side for scientific applications. Just I want to mention that. And so what we are talking about is GNSS station metadata. And the first question is, what is it and why is it critical? So station metadata comprises all the information that defines a station and its instrumentation. And this is very important when we process the data and when we analyze data products. So station metadata include the station ID and country code. This is just a small list, which are important to identify which station we are talking about, which station we are processing. The station ID is important to find the RANX files. As we just heard about, there are many repositories. When you have a station ID, you can find it on different repositories. Sometimes the same names, historically 4 characters, have been used in different countries. So this is one of the issues we face. When the station has the same name, of course, we can rely on the position, but station metadata usually includes also approximate position, and approximate is an important point here. This information is used at the processing level to extract correction models, like I mentioned here, tidal effects, tropospheric delays. Of course, antenna and radome types are very important because they are needed to correct phase center offset and variations. And eccentricity is also important to bring the complete position to the monument marker. So some of the information, some of this metadata can be found in the RANX headers, but experience shows that this is often not reliable. So IGS introduced a standardized file called sitelog file. And this is an example for one station, CCGM, located in a Japanese island. And I will come back to this station in my examples later. So this is why I spent just a few seconds to describe the content here. You have the 4-character ID of the station. I don't know if I can have a pointer here. Oh, sorry. No, this way. And the pointer is, okay, I don't see it here. Yeah. Okay, it doesn't work. So the station ID has 4 characters, the country code, approximate position. These are general information sections. Then you have the receiver description and the antenna section. And in the receiver, I want to point here a change in this station, which was installed in 95, and there was an important change in 2001, where the receiver type was changed from Topcon to Trimble. Doesn't matter which are the maker here. And the antenna was changed as well at that date in February 2001. And we will see that this introduced discontinuity in the time series. So how are inhomogeneities in the GNSS time series related to station metadata? What we observe is that there are often jumps in the time series. We are talking about position time series or tropospheric delays, which is more by interest. And they are associated with equipment changes, also with earthquakes and other changes in the station's environment. Of course, these changes can hardly be avoided, but they should be reported in the data product metadata. And other causes that could be avoided are sometimes use of wrong information at the processing level, concatenation of time series, unless it is documented, and also changing data processing, unless it is documented. So here is an example for this same station, CCGM. The time series from 3 analysis centers, JPL, Spogins, a French consortium, and NGL, a Nevada Geodetic Laboratory. And what you can see is obvious. There is a jump in February 2001 associated with this equipment change I mentioned before. It is mainly seen in the station height on the 2 of the data products. The last one, unfortunately, doesn't show it because there are a few points at the end of the series which probably belong to another station located about 1 kilometer away. So if we look into tropospheric delay time series for the same station, ZTD has actually strong seasonal and day-to-day variability because of the changing weather. So it is quite difficult to see the change. The 2001 change of equipment is located by the vertical bar in green. In some cases, we can see a jump in the formal error, is the case here, connected to this equipment change. Not always the case. And if we want to highlight the change, the jump in the ZTD time series, actually we need to focus on ZTD differences to remove all the climatic variability. So this is an example for the same station where we subtract the ERA 5 reanalysis. Here you can clearly see the jump in 2001, and actually using a reference shows that the period before the jump, there is a bias. And this bias actually, when we inspect which type of antenna radome was used, it does not have a calibration model. So it means that this data have been processed with the antenna only, not taking the radome into account. And this produces a bias of 3 centimeters in ZTD and 10 centimeters in the station height. So there are other examples of jumps and biases connected to using the wrong antenna model at the processing level. This is an example where the antenna change was applied too early in 2008 instead of 2011. There's a 20-meter bias in ZTD. And another example which shows a bias which occurs in the second part of the time series, which is not obviously connected to an equipment change, at least according to the site log information that we have. Of course, the bias, the jump is obvious, and so we suspect that in this case there is wrong or incomplete information in this site log. So then comes the question, how reliable are the information found in the site logs? And we made an analysis of the global, regional, and national repositories. They are not always consistent. What we observe is that there can be a mix of station IDs, 9 versus 4 characters, the names in the site logs connected to this difference in IDs, but also different versions on different repositories, a mix of country names and codes, not necessarily a big issue, and also some differences in coordinates, which are sometimes rounded, but sometimes zero padded. More problematic situations that we found is in about 10% of the cases, there are inconsistencies between the Cartesian coordinates and the geographic coordinates for the station. And sometimes because of typos, can be a difference of thousands of kilometers. So a lot of problems come from typos, but also formatting errors. Yeah, and a more comprehensive assessment of the IGS repository can be found on the Google Drive. Yeah, this is just a comparison for the CCGM station from 2 repositories to highlight the differences. Okay, it's not very important. So we started to solve some of these problems. We started to set up a database of station metadata in collaboration with Formater, the French National Data Center for Earth Sciences. So the goal here is to collect site logs from global, regional, national repositories. Many stations can be found on several site logs, so we can cross-compare the information content. And the idea is to serve quality-assessed metadata, which can be used by our scientific community to process the data, the RINEX data, and also to interpret the time series, as I showed in the examples. And to solve one of the main issues I mentioned is the approximate coordinates. We also download a subset of RINEX files, and we compute the coordinates. We are sure that the RINEX files are associated to the site logs because we take them from the same repository. So we have accurate coordinates, which we use in the database. Yeah, and this is just a few statistics of what we currently have is nearly 30,000 site logs downloaded from 20 sources, 20 repositories. The biggest one is UCSD with more than 10,000 site logs. And what we integrate in the database is 15,000 unique stations. Of course, some of the stations are in different repositories, so this number is much smaller than the previous one. And the more trustable, according to our criteria, repository is M3G, which is operated by the Royal Observatory of Belgium and is connected to EPOS, the European Plate Observatory boundary system. Yeah, and so this is a few examples of the use of this metadata. It was actually the first goal of this work is to have metadata to validate jumps that we see in time series. And this is, again, on the tropospheric delays. The time series show the differences with ERA 5. And the jumps you see are actually detected automatically by a software package that we developed. And metadata help to validate some of these changes. Of course, some cases we don't have metadata, or maybe they are wrong, as I mentioned before. So we apply this method to a different number of data sets. And here to summarize, the results we find from the segmentation are very consistent across the data sets. Some of the stations are about less than 10% are usually homogeneous, means that we don't detect any jump. On the other stations, we detect on average one change point every 5 to 7 years. This is consistent. This is for tropospheric delay. It's consistent also with detections in station positions. And with the metadata, we are able to validate up to 35% of the change points. I want to mention for the NGL data set, the validation percentage is smaller. We explain that this is for different reasons. One of them is that we match only 90% of the stations because they use 4-character IDs. So we don't have the station with the same name. It means they rename the stations. Another reason is that they mainly use metadata from RINEX files. So they may have some extra jumps that don't coincide with real equipment changes. And the third one is they do also some concatenation of stations, because this is not the problem for their own applications, which also introduces some extra jumps, as I showed in the first example. Okay, so to summarize, we have seen that metadata are critical both for the data processing step and the interpretation of time series. We found inconsistencies in the site logs over all repositories up to 10%. Most of them are due to typos, and one of the biggest issues is that it introduces some inconsistencies in the station position, and this is really critical to extract models for the data processing. So one of the key questions is how to improve the fairness of the GNSS products. So improving the fairness of the metadata, the station metadata is one aspect. The RINEX description, as we heard in the talk before, is also another important aspect. Modernization includes also providing machine actionable access to metadata through APIs. And for the time series homogeneity, of course, we cannot solve all the problems with the metadata alone. Homogeneity tests are necessary. And the tools like the one I mentioned, there are many others very useful to check the homogeneity and to correct for the jumps. Okay, that's all from me. Thank you for your attention.